Hi everyone, I'm Stesh Thuli, a PhD student at Imperial College London, and today I shall be presenting my paper titled MetaNet, Automated Dynamic Selection of Scheduling Policies in Cloud Environments. This is a joint work with my advisors, Giuliano Casale and Nick Jennings. So the problem we are trying to solve in this work is as follows. Given several data-driven schedulers or scheduling policies, how do we dynamically decide which scheduler to use for a non-stationary cloud computing environment? And we want to do this such that we optimize the quality of service or QoS of the cloud setup while minimizing the execution cost of these scheduling methods. And several resource management solutions have been proposed in the past to optimize QoS, which particularly focus on optimal placement of tasks on cloud virtual machines or VMs. And such resource management methods have increasingly explored data-driven deep learning-based task scheduling methods. Moreover, these methods typically rely on a trace of resource utilization characteristics and QoS metrics of the tasks and cloud hosts and are typically referred to as trace-driven schedulers. They utilize such traces to train, say, a deep neural network or DNN to estimate a set of QoS parameters and run optimization strategies to find the best scheduling decision for each incoming task. However, most prior work run inference using such trace-driven DNN models on a dedicated broker node to generate scheduling decisions, while the incoming tasks are executed on the worker nodes. In such cases, having a dedicated broker is often cost inefficient due to the idle times between decisions in discrete time control settings, wherein the task placement decisions are taken at fixed scheduling intervals, say, for instance, 5 minutes, 10 minutes, and so on. To tackle this, we resort to paradigms such as function as a service or FAS that allow execution of deep learning schedulers as serverless functions, only incurring the costs for the inference time of each DNN model. Such stateless function calls work in discrete time control settings such as task scheduling, as the decisions are independent. And in such cases, if we consider each DNN-based scheduler as a serverless function and the selection procedure as a task for a worker node, we can work without the broker node altogether, leading to significant cost gains. And this is empirically motivated by the figure on the right. It shows a comparison between cost per task with a dedicated broker node and 10, 50, and 100 cloud hosts as worker nodes. The scheduling policy is run as a serverless function decided by the proposed MetaNet policy. And the broker is a cloud VM, computational capacity of which depends on the number of worker nodes and the complexity of the DNN-based scheduling approach. So how do we solve this in dynamic settings? One way to tackle the above problem is to build a tunable scheduler from the ground up that can make either quick and suboptimal decisions or slow and optimal scheduling decisions. And this tuning parameter that affects this computational requirement can be dynamically updated to ensure cost efficiency. However, in this work, to leverage the recent scientific advances in task scheduling and build a policy agnostic solution, we choose a set of state-of-the-art methods, and this set of state-of-the-art methods could be arbitrary. So this work aims to solve this meta problem of on-the-fly selection of a scheduling policy for a cloud computing environment, wherein the incoming tasks are executed on worker nodes and scheduling decisions are run as serverless functions. And to solve this meta problem, we developed this proposed solution that we call MetaNet. So in this work, we target a standard heterogeneous cloud computing environment where all nodes are in the same wide area network or WAN. And an overview of the system model considered in this work is shown in the figure on the right. Our cloud computing environment consists of multiple VMs that process a set of independent workloads, and tasks are realized as container instances that need to be processed. And they're generated from, say, the sensors and actuators in an Internet of Things or IoT layer and communicated to the compute nodes via gateway devices such as smartphones. We do not have any dedicated cloud broker. Instead, we run scheduling policies as serverless functions or fast functions using platforms such as AWS Lambda or Azure Serverless. And some of the schedulers considered in this work include ARIMA-based forecasting and ant colony optimization-based decision-making method, a deep Q-learning-based scheduler, gradient optimization using backpropagation to input, or Gobi scheduler, which I will describe in a few minutes. Specifically, we propose a novel model called MetaNet, which dynamically decides which scheduler to use to generate task placement decisions, where the scheduling methods are bundled as serverless functions. In terms of our workload model, we consider, as I said, a discrete time control optimization problem. That is, we divide a bounded execution timeline into fixed size execution intervals. And a scheduling decision is made at the start of each interval for all the incoming tasks in the previous interval. And the decision of which scheduling policy to execute, as well as the scheduling decisions, are made at the start of each interval using this MetaNet and the policy that is selected by this MetaNet method. Moreover, we assume that the set of policies to choose from is always fixed in an execution for simplicity. And further, we also assume a fully observable environment, which means that the resource utilization characteristics of all cloud VMs, as well as the running tasks in the system, are known at all times. And these resource utilization characteristics include, say, percentage utilization of the CPU, RAM, disk storage, and the network bandwidth. We create a surrogate model that is a deep neural network. We consider a static set of scheduling policies, and given any system state at the start of any interval, each scheduler produces a scheduling decision for this interval. And the state given as an input to the surrogate includes, say, the resource utilization characteristics of the active workloads in the system, the characteristics of cloud hosts, and the scheduling decision of the previous interval. And now this surrogate estimates the average execution cost for each scheduler, and we select the scheduler for which the predicted cost and QoS metrics are optimized. But let me now discuss the surrogate model that we use, the deep neural network we use as a surrogate for execution cost and scheduling time. So the deep neural network surrogate model is shown here. We have three inputs of our composite neural network, which include the workload characteristics, host characteristics, and scheduling decision of the previous interval. We pass the workload and host characteristics through feed-forward neural networks with ReLU activation in the end, and we then concatenate them together to form a single dense vector representation that encapsulates the current state of the cloud environment. And we encode the scheduling decision as a bipartite graph where the edges are from workloads to hosts. And each node in the graph consists of resource utilization characteristics as a feature vector. This bipartite graph is passed through a graph attention network, and the graph attention network generates another dense vector representation that encapsulates the information required to focus on specific aspects of the state and predict cost estimates. And to do this, we pass the concatenated vectors from the feed-forward networks through a multi-head attention module, with the output of the graph attention network also being used to generate an attended output. And this output vector is then normalized with the input and passed on to two feed-forward networks. The first predicts the execution cost of the cloud VMs, and the second predicts the execution time of the scheduling policies considered in the MetaNet framework. And these two values are then used to calculate the overall operational cost by adding the execution time with the cost of running a serverless function for each policy. This neural network is trained in an offline fashion using traces generated from utilizing all the schedulers in the framework, including the resource utilization characteristics, scheduling decision, execution cost, and scheduling times. Now, although MetaNet is agnostic to the set of policies to choose from, we use a set of diverse scheduling methods in our testbed for, say, consistent experiments. And I shall now describe the policies in increasing scheduling time and also improved QoS. The first policy that we use is called ARIMA plus ACO model, and this is an autoregressive integrated moving average model to predict the QoS metrics, say for example, energy consumption, response time, and latency and things like that. And with this, we also use ant colony optimization, which is ACO based technique to select scheduling decisions. So this is the ARIMA plus ACO model. The second policy is LSTM plus ACO, which replaces the ARIMA part of the first policy with a long short-term memory-based neural network for predicting these QoS metrics. The third policy is decision NN, which is just a feed-forward neural network to predict QoS metrics and also generate scheduling decisions using search strategies. The fourth policy is called semi-direct, which uses dynamic programming to generate scheduling decisions. The fifth policy is what we call graph, which uses a graph neural network based surrogate model to predict QoS metrics and gradient based optimization to generate scheduling decisions. The sixth policy is GOBI, which extends graph with advances such as momentum and annealing to avoid local optima in generating scheduling decisions or running that optimization. The final policy is called GOSH, which extends GOBI further with second and higher order gradients for faster convergence. And for more details on these methods, I refer you to our paper. So let me now concretize how MetaNet works. And this figure visualizes the predicted costs as optimization objective as line plots and dynamic scheduler selection with the background color. And we do this for the top three schedulers in terms of frequency in MetaNet. And the main takeaway here is that in highly volatile workload settings, MetaNet relies on, say, state-of-the-art GOBI and GOSH schedulers, which produce possibly close to optimal decisions and also have high decision-making overheads. But MetaNet falls back on low-cost ARIMA plus ACO schedulers or other simplest scheduling strategies in settings where the workloads are not as volatile or even simpler environment scenarios. So to evaluate the efficacy of MetaNet model on real platform, we perform experiments on a Microsoft Azure based cloud deployment with 10 and more hosts. We consider, say, in the case of 10 hosts, we consider 6 worker nodes in a private cloud or an edge environment that have 4 dual core and 2 quad core machines. And in the public cloud, which is geographically distant location, we have another 4 cloud worker nodes with 2 quad-core and 2 octa-core machines. And for our baselines, we consider, again, the static scheduling policies, so only a single scheduling policy is running throughout, as well as some dynamic scheduler selection policies, which include multi-arm bandit-based policy selection strategy, and another reinforcement learning-based method that uses the same data set that we use to train MetaNet to train a deep queue network that takes policy selection decisions. For our workloads, we use this popular AIoT benchmark applications. And AIoT is an AI-based cloud computing benchmarking suite that consists of various real-world computer vision application instances in the form of Docker containers. And the 7 specific application types correspond to these neural networks that they utilize. So, and these include 3 typical heavyweight networks, including ResNet 18, ResNet 34, ResNext 32.4D, as well as 4 lightweight networks, which include the SqueezeNet, GoogleNet, MobileNet, and MLASNet. And this benchmark has been specifically chosen for our experiments due to its volatile utilization characteristics and heterogeneous resource requirements. And for more details on our experiment setup, I'll refer you to our paper. So when we compare the performance of MetaNet method against state-of-the-art schedulers and other dynamic policy selectors, here you see for a test bed that is scaled 10 times from the 10 VM setup to a 100 machine Azure cloud platform where we deploy these AI-based workloads. The results show that MetaNet method outperforms baseline such that it improves these say execution costs by at least 11%, energy consumption by up to 43%, and service level agreement violations by up to 13% compared to state-of-the-art methods. And to test the importance of the graph neural network in the dual-headed prediction of cost and scheduling time, and also the self-attention module, we modify MetaNet neural network in 3 different ways. So these are the ablation parts, ablation experiments. The first is when we consider a model without the graph attention network, and we call this the MetaNet underscore GNN model shown on the top. And second, instead of predicting the cost and scheduling time separately, we produce a single cost metric as the output of the neural network. We call this the MetaNet underscore dual model. Third, we replace the self-attention module with a feed-forward network to say the test the importance of the temporal trends that that multi-head attention model captures, and we call this the MetaNet underscore attention, the ATTN model. And the results in these figures show a drop in performance metrics for these methods compared to the vanilla MetaNet method, demonstrating the effectiveness of scheduling decisions based on both graph inference, independent prediction of these complementary metrics of execution time or execution cost with scheduling time, and the attention mechanism in the neural network. So we also perform some experiments changing the scale of the setup from say 10 hosts to 50 to 100 cloud VMs. And even then we see that MetaNet outperforms baselines. And the figure shows that the overall execution cost of the MetaNet method, which includes the cost of running the cloud VMs for say workload execution, running these VMs for scheduling as part of the serverless infrastructure, and the selection of the scheduling policies as part of MetaNet or the other dynamic selection methods like multi-arm bandit or DQN. In terms of considering all of these different cost metrics, adding all of them together, the total cost of MetaNet is lowest among all of these different methods considered. So this figure shows the performance of the MetaNet model as we vary the number of VMs in the cloud environment. It also shows the selection frequencies of two lightweight schedulers, Gobi and ARIMA plus ACO, and a relatively computationally heavier scheduler Gauche. And clearly, with an increasing number of hosts, energy consumption also increases. However, the response time and SLA violation rates decrease as the load over these host machines drop, as more worker nodes are available. However, the figure shows that as the number of hosts increases, the fraction of times the Gauche method is selected drops significantly. And this is due to the poor scalability of the Gauche method compared to ARIMA plus ACO. This is because, say, Gauche approach performs higher order optimization over the scheduling decisions. And in such cases, MetaNet approach finds Gauche scheduler not worthy of the additional cost due to higher scheduling times, and thus selects more straightforward methods such as Gobi and ARIMA plus ACO in such a case. So to conclude, this paper proposes MetaNet, a surrogate model-based solution to dynamically select the cost optimal scheduler at each scheduling interval in a cloud computing environment. And to do this, it predicts estimates of task execution time as well as the scheduling time for a set of scheduling policies. And such a surrogate allows us to compute an estimate of the total cost implication of running a scheduling policy without executing all of these policies at runtime. And also allows us to select the one with the least cost estimate. And periodic fine-tuning of this neural network surrogate model allows us to adapt in dynamic workload settings, details of which are in the paper, and experiments with real-life AI-based benchmark applications on a public cloud testbed show that MetaNet gives lower operation cost, energy consumption, average response time, and SLA violation rates compared to state-of-the-art methods. And being policy agnostic, this method can be updated with the latest scheduling policies or even extended to other types of resource management problems or computing paradigms in the future. Thank you for your kind attention. All code and dataset for this work are available on GitHub under BSD license. For any questions, please feel free to email me on s.release20@imperial.ac.uk. Cheers.